Hey there, chemistry team! You ready for video number 6 in our chemical compounds journey? We're going to do kind of an extra one today. I don't always teach this one in any formal way, but I just want to touch on it a little bit. Organic compounds, sorry for swearing, right? They're unavoidable. You're going to spend a whole year, if you're a chemistry major, taking organic chemistry, which is the chemistry of just carbon and the way it connects. Fascinating how carbon can connect to itself seemingly in an infinite variety of ways. And if you start adding on oxygens or nitrogens or sulfurs or something like that, you get this wide array of incredibly cool compounds with amazing reactivities and things you could do. I'm not a real three-dimensional thinker, so it's a little more challenging for me to take organic chemistry, but there's aspects of it that were fascinating, absolutely fascinating. The majority of students just love organic chemistry. That bond's going the wrong way. All right, so carbon you can see connect in many ways. A lot of times, most of the ones we're going to run into in general chemistry are just going to be linear, just carbon connecting to carbon connecting to carbon. Understanding carbon wants 4 bonds. We'll hit that in way more detail when we do Lewis structures later on down the road. Just know carbon likes the 4 bonds. But carbon can actually branch out, kind of like a tree coming up with, little branches coming out and twigs coming out of that. So you can have this base, skeleton here, and then you got a carbon coming off here and a couple carbons coming off there. They can get wide. They can come around and attach in circles and hexagons. We talked about line structures and things like that. It gets cuckoo. So linear branch species, which can affect their properties there. But what I want to look at and just do snippets of, we're not going to do a lot of naming issues or reactivity issues. We'll save that for organic chemistry. But I want you to be able to recognize things, or if somebody throws at you amine or carboxylic acid, you have a basic idea in your head going, oh, I've seen that before. I recognize what that is. And that's going to be in what are called functional groups. So on the next board, we'll talk about just a snippet of different types of organic compounds with a distinct set of reactivities that we can kind of lump into categories. Let's go ahead and do that just so they're in your brain. I'm not going to test you on these in my class. Let's look at some of these categories. And again, just snippets. Spend a little bit more time on the first one, and then we'll just say, hey, here's a picture, here's a picture, here's a picture, here's a picture. Hopefully it'll stick in your brain. So categories are what we call functional groups. It's just a grouping of atoms, commonly non-carbon or hydrogen atoms. If there's an oxygen in there bonded a specific way, a nitrogen or a sulfur bonded a specific way, creates a specific type of reactivity that organic chemists are really interested in. And it's the spotlight of that molecule, right? You could have this huge organic molecule, but just this one little area is where the reactions occur. That's where the game's going on. That's where the action is, right? The rest of it, nobody cares about. All right? So we call those functional groups. So let's start with the most simple form, just the basic hydrocarbons. You got hydrogen, you got carbon. Hey, pretty easy. They're fun to burn or combust for energy. So think of your fossil fuels, things like that. So we're going to break hydrocarbons into 3 different categories, all right, or functional groups, I guess you could say. We'll start with the most simple one where there's only single bonds between carbon atoms, only single bonds. We call those alkanes. Picture this as just the main part of organic molecules. And then if we alter that alkane in any way by adding double bonds, triple bonds, oxygen atoms, then we get a completely new functionality called a functional group. And again, these could be branched or they could be linear, straight chain, doesn't really matter. And we can do expanded structural formulas. So this would be like 4 carbon atoms connected in a row with all single bonds, 4 bonds each. Or we could do the condensed structural formula if we wanted to, even a molecular formula. So if you want to do a molecular formula for an alkane, which we will actually use in general chemistry, because we're going to be doing things like called combustion analysis, where we're going to burn or combust hydrocarbons for energy. We're going to look at those reactions and what happens. So I want you to know the basic alkanes. So on the next board, I'll just go through the first up to maybe 1 carbon to 10 carbons. We won't go beyond that. And you'll know most of those, but I think the first few might be some new terminology for you. So in general, if you've got only carbon and hydrogen for the hydrocarbon in all single bonds, an alkane, the formula is going to be CnH2n plus 2. What does that mean? Well, N is the number of carbon atoms. So if you just take that times 2 and add 2, you're going to get the number of hydrogen atoms. It's pretty straightforward. So let's go through, and if you want to get a jump start on me, just do a part of your paper and just list number of carbon atoms 1 through 10. And then give me the molecular formula. How many, if we got 1 carbon, how many hydrogens would there be? If there's 2 carbons, how many hydrogens? All the way to 10. If we had 10 carbons, how many hydrogens? What would be the formula? And we don't need to draw them out. We're just going to do linear ones. We're not going to do straight change ones at this point. So do that for me real quick, and I'll get that up on the board. Here's my ugly little table. You ready to fill this baby in? I'll help you with the first maybe 4, and then I'm going to pause it and have you do the rest yourself and see how you do. All right, so molecular formula, remember it's CnH2n plus 2. So if n is 1, 1 times 2 is 2, plus 2 is 4. So that will be CH4. We've seen that one before. The root for the name, you'll see this pervasive throughout organic chemistry. You'll see this root. It doesn't matter what the functional group is. This will be the root of the name. And for the functional group, that changes the suffix. For example, when we name an alkane, we take the root of it, which is based on the number of carbon atoms in the main chain, and then we add the suffix again. But we're not going to name organic compounds of different functional groups. I only want you to know how to name the first 10 alkanes. All right, so the root... You've probably watched, Breaking Bad and other shows, right? Meth. So if you that's not what meth means in organic chemistry, right? So when you see the term meth anywhere in an organic compound, that means 1 carbon. So like methyl groups or methane or methanol or methanoic acid, you're going, hey, I see 1 carbon atom there. So we're going to take the root plus the suffix. So we get methane, and that's your natural gas, right? Where we heat, the majority of the gas used to heat your homes is probably methane, would be my guess. That little natural gas, the blue flame. So I'm assuming you guys, probably the first 4, most of you have probably heard of, but now we're just going to formalize them. Okay, if we've got 2 carbons, so N is 2. So 2 times 2 is 4 plus 2 is 6. So it'd be C2H6 or CH3CH3. Okay? So we're doing molecular formulas here. If you want to write those out, let's do those in different colors. Let's do those in blue. I'll alternate them for you. All right, so CH3CH3 or C2H6, and the root for 2 carbons is FETH. So if you hear the term ethane, ethene, ethyne, ethanol, ethanoic acid, right, you're like, oh, 2 carbon atoms. I see that. So this would be called ethane. So when we're doing our Bunsen burners in the lab, it's probably going to be mostly methane, maybe a little bit of ethane in there. Add a little gas so we can smell it if there's a leak. All right, let's go to number 3. If we've got 3, so N is 3, so 3 times 2 is 6 plus 2 is 8. That would be C3H8 or CH3CH2CH3 if you drew it out and got 4 bonds to each carbon. This one, if you're barbecuing on Labor Day, baby, if you got a propane tank, right? Prop is the root for that. So an alkane, all single bonds of 3 carbon atoms, would be propane. Now you know what propane gas is, and these are all gases. And you'll learn in organic chemistry as you increase the number of carbon atoms, that will start to change the forces between the molecules, which changes the state they're in at room temperature. So fairly weak forces between these, so they tend to be gases, but then they slowly turn into liquids and then solids later. As they get bigger and bigger, we'll learn about intermolecular forces later. Let's look at 4. I'll stop at 4 and let you finish the rest. This is my personal favorite. 4. So if we've got 4 carbons, 4 times 2 is 8 plus 2 is 10. C4H10, baby. The prefix for that is bute. Now, I call it but that's because I'm just making fun of my organic chemist friends. I'm being a physical chemist and a general chemist type of thing. It's bute. So you get butane, which is like cigarette lighter fluid. Oh, I thought I had one. I probably shouldn't light one on fire in my house here. But when you chick a cigarette lighter, that's butane in there, and the vapor combusts. When you click it, you get little flames like any. So you get butane. But if you want to irritate your organic professor, just go, hey, Butane, look how you had locks, that booger. And then they'll get me back. We'd like, you got to have some fun interplay between the general and organic. I remember where I went to grad school at UCI, they separated, they had the organic chemists in one building and the general chemists, physical chemists in a totally separate building. I don't know if they did that on purpose. I thought that was pretty funny. So pause it, do the rest for me, and see if you get what I got. I'll pause it myself and fill them in because it's going to take a while. You get it filled out? So we ended at the red arrow. From this point on, pretty easy to get the formulas for C5 to C10. And then the names just start with your typical prefixes for polygons. Pent for 5, hex, hept, oct, non, and dec. Right? It's only the first 4 that are a little more unique-ish to organic chemistry. So you get, and these are straight change hydrocarbons, alkanes, so pentane, hexane, heptane, octane, nonane, and decane. All right, so we can burn any of those for a good amount of energy, get a nice little flame there. You're probably familiar with octane, right? When you're blah, 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 pumping up your car. It's not pure octane, obviously, but they just call it that. There's probably hundreds of different chemicals in there, who knows? All right, so again, all we do when we're naming things, and we're not going to name anything else after this, is take the root, how many carbons are in the straight chain, and then alter the suffix based on the reactive portion or grouping of atoms of that organic molecule called a functional group. So let's just take a snippet of different functional groups and we'll polish this off. Let's look at the other 2 categories of hydrocarbons, and the only difference between these and alkenes, or alkanes, is there's either a double bond or a triple bond between carbon atoms. So if we have at least one double bond between 2 carbon atoms, there could be just one or could be more, we're going to call that an alkene. So they changed the suffix to designate that we got this new functional group in there. That double bond is where that's where the action happens, right? That's where the reaction is going to go. So if I have a 3-carbon molecule with a double bond between carbons, well, 3 is prop, that's the root, and then add the suffix ene. It gets more complicated, it gets longer. You'll see a lot of numbers like 1s and 2s and 3s and commas and dashes and stuff. Not important in this class. It's just used to locate functional groups for bigger molecules. What if I had 10 carbons and I had 2 different double bonds? How do you know where they go? Right? Creates different types of isomers. If you don't specify, you can create isomers or different molecules with the same molecular formula. I could put the double bond here and here, or here and here, and get different molecules. So if you want to make a specific molecule, you have to tell in the name where the functional group is. All right. So is that double bond between carbons 2 and 3? Is it between carbons 5 and 6? So we're not going to worry about that. Yay! All right. What if we have a triple bond between 2 carbon atoms? At least one. There could be more than one, but if we have at least one, like in this scenario, we call that an alkyne, and we just add the suffix yne, right? So this is a 3-carbon molecule, so you get the prop, and it's got a triple bond, so we just add yne. If it was a bigger molecule, we'd have to have numbers and commas to locate where that triple bond is. And these all burn quite readily. Acetylene torches, things like that. There's some common names. You'll learn those common names and the IUPAC, International Union of Pure and Applied Chemistry names, when you get to organic chemistry. I just want you to recognize functional groups. I'm not going to have you name them on my exams. I'm not going to have you write them down. The only ones I want you to know are the basic alkanes. So if I say, hey, propane or methane, I would expect you to know what those are. Let's get on to the functional groups that have non-carbon hydrogen atoms. Let's throw some oxygens or sulfurs or nitrogens in there. Ooh, it gets juicy. Here's probably, I would guess, the most common functional group that you run into everyday life. Everybody goes, hey, let's go get some alcohol. Hey, man, let's get some alcohol. Right? It's like, okay. The problem with that is if you just say alcohol, to a chemist, that could be hundreds of different compounds, right? Do you want to go get some rubbing alcohol, drink that and die? You want to drink some methanol, drink that, go blind and then die? Or do you mean ethanol, which is, your vodka-ish spirits? So you got to be pretty specific when you're talking to a chemist. You just can't say alcohol because you're making the assumption that the person you're talking to knows which alcohol you're talking about, right? So be specific as a chemist. So alcohols are any group with an OH. So it's a carbon-based molecule with an OH group on the end somewhere. So we just call that ROH, R being the rest of the molecule with at least one carbon atom. So we can have CH3OH, CH3CH2OH, doesn't matter. The rest of the group we don't even care about necessarily at this point. That OH group connected with a single bond to this carbon atom, that's the functional group called an alcohol, which has a very specific reactivity. So it puts it in a class of its own, has interesting side effects on your body. Those get the suffix OL. So if I have a 2-carbon alcohol, 2 carbons is eth from ethane, right? So you just drop the E from ethane and go ethanol. If it's bigger than that, if it's more than 3 carbons, then you got to use a numbering system to go, well, where is the OH group? Is it on the 1st carbon, the 2nd carbon, the 3rd carbon, the 4th carbon, right? More advanced than we need to go. But I just want you to recognize, hey, if you got an OH there connected to a carbon with a single bond, that's an alcohol. And most of you are probably familiar with ethanol. That's the spirit that they use, like vodkas, I think 40% ethanol, 60% water, or something like that. Mixes in these infinite number of ratios, and you double that percentage, and that's your proof. So vodka, if you take 40% ethanol times 2, it'd be 80 proof or something. Yeah, pretty straightforward. Let's look at the next one. Let me pause it and pop it up there. All right, next one. I like these ones a lot too. They're fun to utilize in the lab. Carboxylic acids. Now, we've looked at these before when we look at acids and bases. All right, so weak acids, the prototypical weak acids we look at, the organic acids, are carboxylic acids. I think we looked at acetic acid, which is the only one, and that's kind of more of a common name. So these have the suffix OIC acid. So you just take the root of the name, drop the E, and add the oic acid. And these have some carbon-based stuff here, at least one carbon atom, rest molecule. You see a carbon with a double bond to an oxygen with a single bond to an OH. So that looks like an alcohol there, but if you add the carbon with the double bond, it changes its reactivity a little bit. So that group right there is called a carboxylic acid group. If you're into bio and things like that, you probably have some specific type of species you're looking at that have an amine group on one side and a carboxylic acid group on the other side. Oh, I'll let you think about that. And then they react together to form chains of things. Okay, never mind. So here we've got a 4-carbon carboxylic acid. So 4 is the butt molecule, right? So from butane, that would be the alkane, drop the E, put oic acid, so butanoic acid. And it's always on the end. And you can put it on the left or right side, doesn't matter. And these, man, they get nasty in lab. They tend to have really sharp, fairly unpleasant to like really bad odors. But if you react them with other species, you get these little fruity smelling things called esters we'll look at later. So there's some really cool organic reactions you can do. Let's look at the next group. This one you've probably run into before. Now for our class, we've run into ammonia. We've probably smelled that in lab. Woo! Smells like an old cat litter box or hair perm. So if we replace any of those hydrogen atoms in ammonia and put a carbon-based group, like a CH3 or CH2CH3, something like that, we get an amine, just a derivative of ammonia. Now, I still name those kind of an old way of doing that. Again, we're going to be naming these or anything. But you have this carbon-based group with an NH2, and you could actually replace another hydrogen with an R group or another hydrogen. You could take all 3 of those hydrogens and replace them with carbon-based group and get these really crazy-looking amines. So, for example, this one, these are the types of amines we'll be dealing with. Just simple, they call them primary amines. Don't worry about it. That's got 2 carbons. That's eth, right? So that's called an ethyl group. So they call it ethylamine. That's an older way of naming it. There's newer ways of naming it. Don't worry about it, or more official ways of naming it. I'm not going to worry about that. So if I say methylamine, that means you just got 1 carbon, so a CH3NH2. If I say propylamine, you got the 3 carbons with the NH2. We're going to keep it pretty simple. Again, don't freak out. I'm not testing you on naming these or writing these down. I'll usually give them to you. We're going to hit these pretty hard in second semester general chemistry when we look at equilibrium and we deal with weak bases, because all of the weak bases we deal with in general chemistry are amines, right? Strong bases are like sodium hydroxide, potassium hydroxide. So these will come back to haunt us quite a bit later on down the road. So I just want you to recognize them and be familiar that these are your weak bases. Whereas the carboxylic acids are the weak acids. A lot of the weak acids we'll be dealing with. So well, anyway, we'll do that next semester. Let's do the next group. Hold on. This is, if I had to pick one organic group that was my favorite, I would probably pick esters because they smell so good. The smells of like fruits and flowers. This smells so good. Most of the other ones are nasty smelling. And it's kind of a fun way, these esters. There was a lab we did a long time. We do these science nights, and we make all these cool like smells of oranges. Like you take a test tube and you smell it, and it's the smell of orange. But since you're not holding an orange, it messes with your head. You're like, oh, I've smelled that before, like a banana. You're like, I know I've smelled that, but you're not looking at a banana or you're not looking at an orange. You're smelling what looks like water in a test tube. I think, if I remember, this isn't my forte, but I think if you react an alcohol with a carboxylic acid. The carboxylic acid smells nasty. You know, alcohol just has that alcohol smell to it. If you mix those, react those properly, you get a cool ester that's fruity or flowery smelling. It's so much fun. It's going nasty, nasty to pleasant. And so an ester kind of looks like a carboxylic acid. You got the carbon-oxygen double bond, carbon-oxygen single bond. You got a carbon-based group here. If that was a hydrogen, that would be a carboxylic acid. But now we're replacing that hydrogen with another carbon-based group. Now, those R's could be the same or different. That's why they tend to see an R prime there. For example, if I have this ethyl group here, there's your ester, and then we have a methyl group there. So they're different. So in this case, R is the CH3CH2, and the R prime is the CH3. So you can have different types of groups. You could have, you know, cyclic groups, you can have hexagons, you could have crazy, crazy stuff in there that give it different scents and different odors. It's really, really neat. We're not going to get into naming those. Common way of doing it is you name this side, you know, one side and then the other side, put it all together, you get these crazy names. Not important for this class. I just want you to be able to recognize what an ester group and just imprint in your mind. Fruity, flowery smells. Very nice. Very nice. Very nice. This next functional group can be kind of fun. Thiols, in the old day they call them mercaptans, I think. Things like methyl mercaptan, Captain mercaptan. So thiols, I want you to imprint in your mind thiol means sulfur. All right, so if you see a name with thio in it, that means it's got a sulfur atom somewhere. So we're going to get some polyatomic ions we're going to be using in one of our kinetics labs in second semester general chemistry later on down the road. You'll get things like a thiocyanate, right? It's like, oh, I wonder if there's a sulfur in there. So you get, it looks like an alcohol. So think of it like an alcohol, just replace the oxygen with a sulfur, right? The oxygen and sulfur are right, you know, in the same column, so they react in very similar ways. But the main difference to me is the smell. I know, you know what alcohol kind of smells like, but these smell horrible. These are your nauseating. Amines smell pretty bad. Amines are like, you know, rotting fish or stuff like that. So there's like putrescine and all these nasty, you want to vomit all over. The thiols also have, you know, think like skunk and garlic odor. So highly, although I kind of like the smell of garlic. But anyway, so very, very unpleasant odors. Very unpleasant odors up there with amines. This is so bad. All right, let's look at another group. These are fun. Aldehydes are pretty sweet, no pun intended. They have a very sweet smell. I think there was the one that smelled like, I love the smell of maraschino cherries. You ever open up a jar of maraschino cherries and just smell it? Or almond extract or something like that. Aldehydes have those pleasant smells. Up there with not carboxylic acids, esters. Esters and aldehydes usually have you're just like, oh, I just want to taste it a little bit, and then you die. Don't ever taste chemicals in the lab. I don't care how good they smell. So here you've got the R group, the rest of the molecule, with a carbon-oxygen double bond with a hydrogen just dangling on the end. If that was an OH, that would be a carboxylic acid. So you can see the subtleties, how close they are. Changes all the reactivities, properties, smells, everything. And they have the suffix al, so they commonly get confused with alcohols. So this has 3 carbons. That would be propanal, right? If that was just an OH group, you get the propanol or something, right? But then when you start getting big compounds, you got to locate where things are. So at least alcohols can be anywhere. The OH group could be on any carbon because it's just dangling off with a single bond to the carbon. Whereas aldehydes are always on the end. They're terminal. All right, let's look at a twist of these. Okay, a cousin to aldehydes are the ketones. They look pretty similar, but for an aldehyde, one side's an R, and the other side's an H, whereas the ketone, you have an R group on both sides. You have a carbon group on both sides. So that carbon-oxygen double bond's in the middle somewhere, and you got carbon-based groups coming out on either side. Aldehydes are on the end. So ketones, I've seen several different ways to name these, right? End in O-N-E, not important. So here's a 3-carbon ketone. See the carbon-oxygen double bond? You've got a carbon group on this side, carbon group on that side. So 3 carbons, prop, comes from propane, propanone. Common name, acetone. I wanted to put that up there because when you get to organic, you're going to get to know acetone really, really, really well. It's a great solvent they use for cleaning things over there. I learned that as like dimethyl ketone. It was kind of an older way of naming where you name the 2 hydrocarbon groups on either side, name this one and this one. So you have like ethyl methyl ketone and all these weird things. So you'll learn all this crazy stuff in organic chemistry. Let's do maybe 1 or 2 more and we'll call it a day. This video is getting kind of long. Let's polish this off with 2 more. And there's more than this. I mean, it goes on and on and on. So have fun in organic chemistry. That's why it's a whole year's worth of stuff. And we haven't even talked about reactivities, just recognizing functional groups. So we have amides, where you've got the carbon-oxygen double bond. You kind of see that, through a lot of these. And then you've got a single bond to a nitrogen group there. And these hydrogens, you could replace those with carbon-based groups as well. So it's almost like an ester, sort of, but with a nitrogen instead of an oxygen here. So for example, here we've got the methyl group on this side. We got the nitrogen there with a methyl group hanging down. That could be NH2. I could replace both of those hydrogens with different carbon-based groups. They can get pretty crazy. Naming those, not so fun, so not important. But you get that amide, you get the C double bond oxygen, C double bond, single bond nitrogen there. So you can see that what makes it unique versus the other ones. And last but not least, you got the ethers, right? Not the mysterious ether back in the old days, where you've got an oxygen singly bonded to 2 different carbon-based groups. So similar to a ketone, where the ketone has a carbon double bond oxygen with a carbon-based group. Here, it's a chain of carbons with an oxygen right in the middle there. Tend to be pretty volatile. I've heard some horror stories of ether fires where these caught on fire in a hood or a back room or something. Not good. So here we've got a methyl group on both sides. So they call it like dimethyl ether. You can get like a ethyl methyl ether. You can get these weird things going on. But I think that's enough pain for now. Gives you just definitely know the 10 alkanes. That's all you need to know for this class. But just get a feel for the other functional groups just so, when you get to organic, you go, I heard that before. Maybe review this video before you take organic chemistry as well. You guys rock.